Okay, so today we are pleased to welcome Robert Todd from the Woods Hole Oceanographic Institution up on Cape Cod. He is currently an associate scientist at WHOI, well, I'll start at the beginning, I guess. He got his BS in physics, applied mathematics, and marine science at UNC State not UNC, North Carolina State University.
That's an important difference.
Yes, very, very different. And then went on to the Scripps Institution of Oceanography in 2011 and got his PhD, or no, he got his PhD in 2011. He went on to Scripps in 2005. He overlapped with me at Scripps. I was at Scripps from 2006 to 2012. So I was a postdoc and he was a student, and that's how we met. After that, once he got his PhD, became a postdoc at Woods Hole, and then sort of worked his way up and became an assistant scientist by 2013, and is now an associate scientist starting 2017. And Robert has been doing work with gliders since I've known him. He started out off the coast of California, looking at the California current, and then when he moved out east, he was refocused on the bull in the china shop out here, the big guy in the room, the Gulf Stream. But he's also done a lot of work in other parts of the ocean, including the Indian Ocean and the tropical Pacific. He'll get into this, but one of the cool things about gliders is that they're able to be out there all the time and for long periods of time, and so you can see things that you might not see otherwise. For instance, you can watch hurricanes go over the Gulf Stream and see what they do to the water, which typically your standard ocean-going observer would not try to do that. But with that, I'll turn it over to Robert, and he'll tell us about the insights gleaned from observing the Gulf Stream.
Great, thanks, Christopher. So happy to be here. Testing out, you guys are my guinea pigs for an all new talk putting together. So hopefully I've put it together in a sensible way. So as Chris said, I'll be talking about the work we've been doing for the last several years now with gliders surveying the Gulf Stream. This is work, make sure I mention them now in case I mess up and forget later. But I've got two students involved with, Jolene Heidrich and also Lieutenant Kyle Couch, who's a Navy student. Both are MIT WHOI Joint Program students who are working on this data with me, and also play a big role in going in the field and helping collect the data as well. And also get the most important acknowledgements out of the way here at the beginning too. We've been doing these observations now for more than 5 years. That's taken quite a bit of funding support from various agencies. So NSF has been a big player, NOAA has been a big player, ONR has sponsored the work. We've also had some philanthropic support from Eastman Chemical Company, and WHOI even stepped in at the beginning with some of the seed funding to get things going. Without all of that support, none of this would have happened. So the Gulf Stream, let's see, why doesn't that work? Why can't my slides change? That's interesting. There we go. Okay, so why study the Gulf Stream? So I'll start out. So the images here are, I don't think anyone has seen a picture of the Gulf Stream like this before, because I just made it recently and there aren't many data sets available to make a picture like this. So this is a purely observationally based, three-dimensional look at the temperature on the left, the salinity in the middle, and the absolute velocity on the right of the mean Gulf Stream over the past 5 years. I say unlikely that anyone's seen this because most pictures of the Gulf Stream you're going to see, most motivational pictures might be an SST image, which you see the beautiful warm water flowing on the coast, or you may see individual transects across the stream, but to have this three-dimensional coverage through the upper 1,000 meters is a pretty unique feat of the glider observation. So why we study the Gulf Stream? So the Gulf Stream is the western boundary current of the North Atlantic. So it's in the basin scale picture, it's the northward flow in this narrow boundary current, quite swift. that's balancing a broader spur-driven flow over the rest of the gyre that flows towards the south. It carries with it warm, salty water of tropical or equatorial origin. You can see that here in the temperature and salinity fields. You have quite warm water at the surface, and even well down at depth, the Gulf Stream itself is quite warm. And you have quite high salinity. Actually, the highest salinity water in the stream is actually subsurface. So this is at the 200-meter level. You can see the highest salinity. Those are salinities approaching 37 PSU, which is quite salty. It also, so that's the Gulf Stream plays a role there in the gyre circulation. It also plays a role in the meridional overturning circulation in the Atlantic. So there's this thermohaline driven flow where you have deep waters that are formed in the high latitudes and that sink and flow, particularly the ones forming in the North Atlantic, flow equatorward. That transport has to be balanced by a return flow to the north. And so the Gulf Stream is the upper limb, part of the upper limb of that Atlantic meridional overturning circulation, or the AMOC. The Gulf Stream along the East Coast flows through several different dynamical regimes. So down in the south, off Florida, you can kind of tell here, so this is the bathymetry plotted in gray. Off Florida, it's actually flowing through a channel. It's confined to a channel. Once you get beyond or north of the Bahamas, then it's flowing along the continental margins with a stabilizing boundary that it flows against, but then it gets up to Cape Hatteras and it leaves the continental margin and flows out into the open North Atlantic, where it begins to meander as a free jet in the open ocean. So we have these, over this sort of 2,000 kilometer range, we have various dynamics at play. The stream, by being a very large and very powerful current, plays a big role in shaping the coastal circulation, and I'll talk a bit towards the end of the talk about how it modulates shelf deep ocean exchange, so waters flowing from the continental shelf into deep water. And then the Gulf Stream is also a place where these subsurface waters or waters that get subducted into the center of the ocean basin tend to form. So we call those mode waters, and those are important because when waters last see the atmosphere, that's when their properties are set. So these are waters forming at the surface, particularly absorbing carbon dioxide from the atmosphere and then sequestering that carbon dioxide into the deeper ocean. So it plays a role as well in removing carbon from the atmosphere. So the other big motivation for the work I've been doing is to fill an existing gap in our sustained observing effort of the Gulf Stream. So we know the Gulf Stream is important. So as a major feature of the ocean circulation and the climate system as a whole, we need sustained observations of its structure to know what's going on. We need that support, to support basic science, and also to support things like modeling the ocean, forecast modeling, hurricane modeling, search and rescue modeling, all of these things. If you don't have the Gulf Stream right, you're not gonna get the results you want for any of those end user cases. So just to orient you here, I'm now showing this is just the map of the East Coast, and I've pulled out just the surface velocities where they're strongest from the plots I showed on the last slide, just to give you a sense of where the Gulf Stream flows. And so my observations end about here, but of course the Gulf Stream carries on. So this gray line that you'll see, and you'll see this line throughout plots throughout the talk, is the time mean position of the 40 centimeter sea surface height contour, which does a very nice job of following the path of the Gulf Stream. So it's just an indicator of where the core of the Gulf Stream typically is. So the multi-decadal backbone of our observing of the Gulf Stream has been a collection of observations, the oldest being down here in the Florida Strait, where actually they use submerged cables, really telephone cables between Florida and the Bahamas. And by measuring the voltage induced in those cables, you get an estimate of how much water is flowing through the Florida Strait. So that's a measure of the volume transport of the Gulf Stream where it originates in the Florida Strait. So that's been happening now for coming up on 40 years. Much further downstream, some 1,500 kilometers downstream, there have been over the years, there's three programs I'll focus on. One, which hopefully folks know about in this audience is, of course, the Oleander line. So that's a container ship running back and forth from New Jersey to Bermuda weekly or every 2 weeks. Charlie can correct me on the exact detail there. Been doing that since 1992. The ship is equipped with both expendable bathythermographs. These are little probes that drop off the back of the ship and measure a profile of upper ocean temperature through the upper few hundred meters of the water column, and also a Doppler current profiler, so an instrument mounted in the bottom of the ship that measures the currents as the ship steams across the Gulf Stream. There's another line of those XBTs, the bathythermographs, that goes from Puerto Rico into the New York area, gives another transect-adjusted temperature. And then for 10 years, from 2004 to 2014, there was also this line called Line W, operated by Hui, that had both moorings and semi-regular research vessel occupations, where they measured it. So the ship went along the line. These are the dots, are the stations they measured frequently, and then there were also a series of moorings that were out there continuously across the stream. So these data sets are all great. There have been these are just representative papers, recent papers from each one. These are great long-term data sets. The one kind of obvious caveat is that there's a 1,500-kilometer gap between those sets of observations. And we just talked about how from the Florida Strait to here, the Gulf Stream is transitioning from this jet confined to a channel to a jet flowing over the deep sort of order 1,000 meter, 800 to 1,000 meter deep Blake Plateau region along the continental margin and then out into the open ocean. So there's a lot going on with the Gulf Stream over that distance that we don't have the sustained observations of. So you might ask if you're familiar with the Ocean Observing System, a big player in that for the last 20 years has been the ARGO program. So that's a program that uses these small cheap by oceanographic instrumentation standards, profiling floats that go out and go up and down. So every 10 days, one float will make a profile from 2,000 meters to the surface. Then it will spend about 10 days drifting at 1,000 meters and then repeat. And each float does that for several years until its batteries run out. So the ARGO program was designed to cover at sort of broad scales the ocean basins. And it does a really great job of doing that. So the map here is showing some 7,500 or so ARGO profiles over the last 5 years in this region. So looks pretty good. It does a nice job filling in on the broad spatial scale between these other fixed in space observations. But if you keep in mind this is over 5 years to get all of these profiles, the actual spatial resolution is relatively coarse. Nominally, ARGO has a profile every 3 degrees in latitude and longitude. And they're also, because the floats drift at 1,000 meters, the floats tend not to make it up into the shallow area. You see there's very few floats in this region over the Blake Plateau. A couple of floats have managed to get in there, and a few have ridden along the Gulf Stream, but there's pretty poor data coverage in the shallower water because ARGO wasn't designed to do that. So that's where the gliders come in. So we've been doing this now since, there were some gliders before 2015. We've been doing this regularly since 2015. So now the orange dots are all of the locations of all the glider profiles in the same 5-year period as the ARGO, the dots for the ARGO program. You see now there are something like 3 times as many profiles, and because we're focused on the Gulf Stream, the resolution is much, much higher along the Gulf Stream. So the gliders are providing this high cross-stream resolution. That's something we really need to look at the strong front and the strong gradients associated with the Gulf Stream. And it's doing a pretty nice job, I think, if I do say so myself, of filling in between these other observations. So it's filling this gap in the observing system. So now an outline of the rest of the talk. I'll tell you a bit more about how we go about collecting these observations with gliders in the Gulf Stream. Then we'll focus on a few different particular science results. So first we'll look at what we've learned from the glider observations about volume transport in the Gulf Stream, both in the time mean, and I'll look briefly at how hurricanes impact the transport. Then we'll spend some time looking at the kinetic energy in the Gulf Stream. And so those two are both kind of the large scales of the whole extent of the Gulf Stream. And then we'll zoom in and look at some of the topographic effects happening where the Gulf Stream runs over relatively shallow bathymetry. And then finally, if I haven't completely run out of time, we'll look at shelf deep ocean exchange at Cape Hatteras and the role that the Gulf Stream plays in that. And I should say, feel free to interrupt if you have any questions along the way. I probably won't notice any hand raises through Zoom, so just feel free to shout out. So we'll start out with the how we make these observations. So for those who want to watch the movie, enjoy. That'll just show you since 2004 where gliders have gone along the U.S. East Coast. The gliders that I use are so you've seen a picture on the first slide. Here's a schematic of one. And then this figure is a schematic of one dive cycle for these gliders. They're called spray gliders. It's one of several types of these buoyancy-driven vehicles. So the way they work is they change their displacement, they change their volume by moving oil from an internal reservoir to an external reservoir. That makes the glider either sink when all the oil is inside, or it's able to rise by pumping the oil back out. So one dive cycle for a glider starts at the surface, where it gets any new commands, then it decreases its buoyancy, it descends. These gliders can go to 1,000 meters. It takes them something like 3 hours to get to 1,000 meters. As they're descending, they pitch their nose down, so they glide forward on their wings, and they can steer by rolling. They get to 1,000 meters, they pump the oil out, and they come back up. Now they have their nose up, so they continue gliding forward. So they glide forward at about 1/4 meter per second, or half a knot, which is really quite slow. And the fact that they're quite slow is particularly important in the Gulf, with working in the Gulf Stream. That's why you see, if you watch the movie, we have done most of our deployments from Miami, and we admit that we are not nearly as fast as the glider is not as fast as the Gulf Stream. The Gulf Stream goes 1 meter per second or faster. So we deploy upstream, the gliders steer across the current as they're advected downstream, and we get across the current, we turn around, and we do the same thing. So we end up with these zigzagging profiles from Florida up to New England. So one mission typically lasts about 120 days, so 3.5 to 4 months. And we've now done, so counting in a second project called Peach, which is a focus project on Cape Hatteras, which is you see all these gliders for 2 years right at Hatteras. Counting all of those missions together, we've done more than 40 missions and more than 3,000 glider days. So we have over nearly 10 years of observing effort in less than 10 years of actually observing, because we also have more than one glider in the water and more than 22,000 profiles. So what do our observations look like? So this is one of some 200 cross Gulf Stream transects we've collected. So each glider is equipped to measure the temperature, the salinity, the absolute velocity. So we have a small Doppler current profiler mounted on the glider, so we can measure not just the geostrophic velocities, but the absolute velocities in both directions. We carry a chlorophyll fluorometer, so we get some idea of what the phytoplankton population is doing. We, on a few gliders, not nearly all of them, we've had a dissolved oxygen sensor, so we can get an impression of one part of the biogeochemical field. And because we have an ADCP as an acoustic instrument, we also get acoustic backscatter, and our instrument is a 1 megahertz system, which means we're bouncing sound off of things that are order of millimeter in size, which tend to be things like zooplankton or silt. So you can actually see both of those in this particular image. This sort of up and down cycle you can trace is the zooplankton moving up and down. They move down at night to hide in the darkness. They come up in the night to feed in the shallow waters. You can see that diel migration. You can also see this really high backscatter. This is actually silt. This is where the Gulf Stream has just left the continental margin. There's a bunch of silt that's picked up, and that's raining down and sinking out as the Gulf Stream flows away from the continental margin. And so to give you an idea of the horizontal resolution, the tick marks here are showing where we have each individual profile in this transect. So like I said, we have more than 200 of these transects. So one other point about the data I want to make, one other point I'd like to make is that all of these data are made publicly available. So the gliders, every time they come to the surface, so every 6 hours or so, the glider sends back its data. And so within a few hours of that, we send that data out to operational users. So those are like the Navy uses the observations to assimilate in their operational models. This IUS is the U.S. Integrated Ocean Observing System. Goes out, they feed the data out, because there's a lot of other users that way. And we even send it out to this GTS, the Global Telecommunications System, which is where like the weather forecasters, the National Weather Service, forecasters in other countries as well, get their data and then go into forecast models. So that's the near-time data go out for operational use. Then after the gliders come back in, so after the 3 months or 4 months deployment, we fully process and quality control all of the data, and then we make those data as well available in a pretty convenient format that meets a bunch of archiving standards and becomes citable using a simple DOI that we're all used to. I just wanted to show one quick plot of that the real-time data do have an impact on the models. This is an example from Lieutenant Kausch, who's a Navy student working with me and using the Navy's operational model for the year, in this case, 2017. And what you're looking at here is the change in the surface salinity that the model predicts from a 1 day ahead forecast valid on a certain day to the nowcast valid at the same time. The reason the model might change from the forecast to the nowcast is principally because more observations became available to the model to force it to look more like the real ocean. So in this case, we see a big impact in this near surface salinity. The biggest impact is right along this line where I mentioned we had that project focused at Cape Hatteras. We had gliders going back and forth all the time right here in an area with big gradients in salinity. And we see a big impact in the model there. And then we see that impact spread off to the northeast, consistent with sort of an advective signal. So we're fairly certain that this is a case where our observations were impacting this actual operational model that the US Navy is using every day to inform their decision making. So that was a nice demonstration there of why we provide these observations in real time. So moving on to talk about Gulf Stream volume transport. So this is an old question. One of the fairly original questions for oceanography along this part of the world is how much water is the Gulf Stream carrying? We've known since very early times that there was a strong current along the East Coast. There are famous maps by the Ben Franklin and the Folger maps from the 1700s of the Gulf Stream. We've known it's there. This problem with how much water is the transport's been around for a long time. So there have been many prior estimates. So what we're showing here in this plot, and we'll start adding more things to this plot in the next few slides, are so zero here is basically just zero distance is basically Miami, and Cape Hatteras is around 1,400 kilometers, I believe, and then 2,000 kilometers gets us down past Oleander and Line W. So what we're showing here are all of the transport estimates, so mean transport, and these are ones we're looking for estimates that come from data lasting more than observations of more than a year in duration. The black points here are the ones down here to the south are full depth, where the Gulf Stream is flowing over bathymetry that's less than 1,000 meters deep over in the Florida Strait and over the Blake Plateau. The black points down here are estimates of the transport in the upper 1,000 meters. So that's going to agree with the transport estimates we're going to make from the gliders, which sample to 1,000 meters. And then there are a few other estimates we've thrown in here that are to different depths, so either shallower or deeper than 1,000 meters. I think these actually are all deeper than 1,000 meters. So from these disparate estimates, you can pretty clearly see that the transport of the Gulf Stream increases as it goes downstream. That is not at all a new finding. We've known that for many years, that the Gulf Stream roughly triples in its volume transport from the Florida Straits to by the time it gets into well east of New England. But what's a little more challenging with these is we have these various estimates, but they're all using disparate techniques. Some are ship-based, some are profiler-based, some are cable-based. They're from different time periods, and they're over different depth ranges. So while we can qualitatively see that the transport's increasing, and that's a very robust result, it's a little hard to compare, or there's a lot of comparing apples and oranges here. So this is work from my student Jillian Heydrich in her thesis that she's finishing up this year. We have taken all of the glider transects, so plus the transects from the ships going along line W. At the time, we put cutoff for this paper, we had about 160 crossings of the Gulf Stream that went all the way across the Gulf Stream that we could use and calculate the transport. So it actually turns out that estimating transport from individual transects is not a trivial task, because it fundamentally comes down to, you have a transect of velocity. So I'm showing here the one component of the velocity for one particular transect, and you have to decide what exactly is the Gulf Stream in that transect. You know, if you're looking at a mean transect, the Gulf Stream is usually pretty easily definable as this well-constrained jet. You can integrate from a zero contour on one side to a zero contour on the other. But with these individual transects, things are a good bit messier. So we spent a lot of time working out using some image processing techniques to identify connected regions of flow in the same direction. So that's what this black boundary is outlining, is the flow. All of this flow is in the same direction. But there might be, and then determining which of those regions of connected flow should be the Gulf Stream. We take the one with the most transport, which is this orange section. And you might note the next area of connected flow is this little dinky weak flow over here that only totals 1/10 of a sphere drift. A sphere drift is 1,000,000 cubic meters per second, whereas this one that is the Gulf Stream in this case is about 27 sphere drifts. So that's for one transect. We have an estimate of the volume transport. We do that for all of the transects, and we get all of these blue dots and blue squares. So the dots are from the gliders, the squares are from the ship-based estimates. They're all treated the same way, with the exception of the open circles are for the few glider transects that we don't have direct velocity measurements, and we use geostrophy instead. But you can see there, those particular ones that aren't outliers or anything. So you look at that, again, we see, as we would expect, the transport is increasing with a long stream distance. It's, again, not news. But there's also a ton of variability. So at a long stream position, say 1,000 meters here, we have quite a lot of variability in how much transport there is transect to transect. And that could be due to eddies. So maybe they're co-rotating and oppositely signed eddies adjacent to the Gulf Stream that we might have that are influencing our transport estimates. There's intrinsic variability in the Gulf Stream itself, and there can be variability in the forcing, like the hurricanes that I'll talk about a little bit later. So what we can do to clean this up some is we can pass over all these individual estimates with a Gaussian weighted running mean. So we put a longshore scale of 200 kilometers on that, which is kind of that scale comes from both the spacing between our transects, as well as it's kind of a typical scale of meanders in the Gulf Stream. So that's how we get this blue line, and also how we get the arrow bars. And this blue line now is our estimate of the time mean transport of the Gulf Stream as a function of a long stream distance. And you can see it in the mean, it agrees pretty darn well with the prior estimate. So that was reassuring to us, that the gliders really are a valid platform for measuring transport in the western boundary current. I don't have the slide, I won't show it in here, but I will tell you that the transport increases, but actually the transport weighted speed, so a measure of the average speed of the Gulf Stream.
You can't look at it and see it.
Sorry, say again? Maybe not. So the transport weighted, the speed of the stream is actually fairly constant over this 2,000 kilometer range. So from that, we can infer that it's actually the cross-sectional area that's increasing primarily. We know it's well known that the Gulf Stream gets deeper as it goes along, but we can't, from our observations, infer whether it also gets wider because we're obliquely crossing the stream. So that was a nice result, that we get transport estimates that agree well with prior estimates, and we can fill in the gap between them. But what we can also do that's a bit more unique, because the gliders measure not just velocity, but also the temperature and salinity at all the same places, is we can partition that volume transport into different water classes. I won't call them actual water masses in the oceanographic sense, because we're going to use much broader definitions because we're going to divvy the volume transport up into a relatively few number of boxes, such that we include all the volume transport. So this temperature salinity diagram here, the background or the red colors are a probability density function of temperature salinity. So showing you, so where it's brightest, that's where we see that type of water most commonly. So you can see that there's 18-degree water. This is the mode water, the subtropical mode water of the North Atlantic is the big mode in the distribution. And we also see there actually at depth, there are two different intermediate waters. There's upper Labrador seawater and Antarctic intermediate water, these two distinct tails. So you have a pretty wide spread near the surface. Very fresh waters coming from the mid-Atlantic bight, saltier waters than the surface waters coming from in the Gulf Stream and coming in from the Sargasso Sea. So we divide up our transport into these different water classes. So surface water, waters in the thermocline, the subtropical mode waters, and then ill-defined intermediate waters in these two other named intermediate water types. And we get a plot that looks like this. So the top edge of this is the same total volume transport, but now you can see which types of water are making that, and particularly which ones are contributing to the increase in transport. And it's not the near surface waters that are changing that are adding transport to the Gulf Stream. Those are pretty constant. It's these subthermocline waters, particularly the subtropical mode water, like the 18-degree water, that grows from, say, 15 or so spherodrops in the Florida Strait to some 40 spherodrops by the time we get down in the neighborhood of Oleander and Line W. And then also the upper Labrador seawater, that's this green right here. We see none of that in the Florida Strait. That water is coming from the Labrador Sea and the North Atlantic. It's coming down along the coast and then getting entrained into the stream after the Gulf Stream gets north of the Bahamas. And you see that volume transport growing as we move towards Cape Hatteras. The other interesting one, and this is stuff that Jolene is working on now, is this Antarctic intermediate water. This stuff is coming all the way from the other pole, has made it up the Gulf Stream, peters out as the Gulf Stream flows over the Blake Plateau. And the short story there is it gets mixed away by the topographic effects that I'll talk about a bit later. So just to look at one, so that was about the mean, to look at one example of why we see all of this variability. So this is the same plot again of all the individual transport estimates. And there's one particular outlier here that happened in September. This was a transect in late September, early October of 2017, when the transport at sort of off the coast of Georgia was less than 20 spherodrops. That's very low. That's some 50% less than it normally is that time of the, or normally is at that location. And so September, October 2017 was a pretty active time for the North Atlantic in terms of hurricanes, although it doesn't hold a candle to what we see right now with, I think, 5 named storms in the Atlantic. But if you remember 2017, we had Hurricane Irma that made a huge mess of the islands in the Caribbean, and then made a landfall in the Florida Keys, and then a final landfall on the west coast of Florida. Then just a couple of weeks later, we had Hurricane Jose and then Hurricane Maria passing seaward of the Gulf Stream along the East Coast. So the plots here are the tracks of the storms and their wind speeds. So a hurricane is anything above 64 knots. So you can tell when these were hurricanes until near the very end. And at the same time, we actually deployed a glider from Miami just as they were instituting mandatory evacuations out of Miami. We got the glider in the water, and our guys promptly got on the plane and got out of there very quickly. Turned out to be a fortuitous deployment because we had multiple storms coming through, and so the colored segments here are individual cross-stream transects measured by that glider. We'll look at transect 3 to 10. This happens to be transect number 6 with the very low transport. Excuse me. So if we look, there were 2 effects that happened. So one is this low transport, and we look at the velocity fields from transect 3 through transect 10. So this is time increasing to the right. We see particularly transect 6 here, much weaker velocities. It's over the full water column depth. So I had 18 spherodrops of transport compared to 30 or more spherodrops upstream of that, and 30 to even more downstream. So we had this full depth flowing of the stream for a period of about 2 weeks. It turns out that was correlated with storm-induced winds blowing against the Gulf Stream and also some positive wind stress control from the storm. The other effect we saw was this, and it happened a little bit later, a week or so later, we saw this very fresh water within the core of the Gulf Stream. So if you look, the core of the stream normally is fairly salty, salinity is well above 36. Here I'm outlining in white is the 36 PSU contour, and the salinities are quite a bit lower than that in these 3 transects. It turns out you can track that water back, or the timing of that water arriving there back, and it looks like that's rain from Hurricane Irma. Hurricane Irma was on the west coast of Florida. So rain either falling on land and washing offshore or falling directly on the ocean. That was then entrained into the Gulf Stream, and a few weeks after Irma made it along the US East Coast in the surface layer of the Gulf Stream. So that's just a one quick look at how hurricanes impact both the volume transport of the stream and the properties of the water transported by the stream. So from there, I want to move on to talking about mean and eddy kinetic energy. So, most people, kinetic energy is the energy of motion. So in this case, it's the energy of the ocean moving. So it's a pretty key metric of the ocean circulation is how much kinetic energy is in the ocean. It's both of the ocean and the entire climate system. So we're going to find 2 quantities: the mean kinetic energy, which is and we'll ignore. This is pretty typical for ocean kinetic energy. We ignore the mass or the density part of it, and we just look at the mean kinetic energy. It's just 1/2 the amplitude of the mean velocity. So my angle brackets here are averages. And the eddy kinetic energy is going to be based on the perturbation velocities, where we define the total velocity as the mean plus the prime. It's important when you do any sort of estimate or look at things where we're talking about an eddy term in the ocean or the atmosphere for that matter, that the choice of your averaging operation, my angle brackets here, really defines what I mean by an eddy. So on the next slide, I'll spend some time explaining what my choice of averaging is for the glider observations. So if we look at, these are a few global maps from, this is a map from remote sensing from sea surface height, surface velocities. This is in situ, this is surface drifters actually measuring the velocity, and this is from a coupled model. And they're all showing the eddy kinetic energy estimated for this product. And you can see that they have pretty similar broad scale patterns, but the magnitudes vary a fair bit. This is a log scale. But in all of them, you can see the western boundary currents. So the Gulf Stream, the Kuroshio, the Agulhas, the Malvinas over here, the East Australian Current, are all large reservoirs of eddy kinetic energy. And they're also large reservoirs of mean kinetic energy because they have strong velocity. So there have actually been relatively few estimates of Gulf Stream eddy kinetic energy in the past. Here are a couple of early ones. This is one by Phil Richardson from 1983 that combined observations at all of these dots and triangles and things to make one section across the full depth Gulf Stream at 55 west. So this is well to the east of the continental US, but a full depth section of eddy kinetic energy. And you can see the highest eddy kinetic energy is laterally. It's in the core, kind of centered in the core of the Gulf Stream, and it decays from its highest values at the surface to depth. So there, the units here are centimeters squared per second squared. So I will switch to meters squared per second squared in my plot. So you have to move the decimal place over 4 places. So that's a transect. So that has one horizontal dimension and a vertical dimension. An alternate here is from Breck Owens using a bunch of acoustically tracked floats that were drifting at 700 meters, and he was able to put together a 2-dimensional map of the eddy kinetic energy in the Gulf Stream region. And again, you see a high values concentrated along the Gulf Stream, but those floats drift at discrete depths, so you can't get this full 3-dimensional picture. And that's kind of the story with the other existing estimates. They're either typically limited to 2 dimensions, and or they may be limited to fairly short timescales. So I've taken all the glider observations in and set out to make a 3-dimensional estimate of the mean eddy kinetic energy for the Gulf Stream along the US East Coast. To do that, I need to figure out a way to take all these observations that are sort of randomly spaced. I mean, they're not actually random, but they're not all at the same place. So it's not that straightforward to just compute an average. So the choice I made was to use a weighted least squares fit on a 0.1 degree by 0.1 degree by 10 meter grid. And so I'm going to define a weight function that has some along stream scale and cross stream scale that are different. So it's anisotropic, because I know that because we have a strong advection, strong flow in the Gulf Stream, that things are going to be stretched out in the direction of the flow. And I'm also going to allow that weighting function to vary spatially, so it's inhomogeneous, both because the Gulf Stream itself is located in some places and not in others, and also because our sampling density varies spatially. So it's a bit of an involved calculation, but the plot here on the right, the circles here, or the ellipses, are indicating what that weight function is shaped like at each grid point or select grid points. You can see it's long and narrow in the core of the stream. So we're honoring that advective scale in the direction of the flow, but also not averaging so hard that we smooth out all of the cross stream gradients. But then as we get out here to the edges where I have less data, we have a much bigger averaging circle to get enough data. The end result is that I get at each grid point, so this is one slice at 10 meters, I get a view of the mean velocity field. So this is the velocity field I showed on the first slide here now. So color is the speed, the vectors are giving you the direction. And it sure looks like a Gulf Stream. The red line here is that mean sea surface height contour. So the paths agree quite well. They even capture features like this little area where it leaves the continental margin because of some bathymetry that we'll talk about later. So I was pretty happy with these fields. And so I have them not just at the surface, but all the way down to 1,000 meters. So given that averaging operator, I can then also compute the differences at for each glider profile. I can compute the difference from the mean, that's my primes, and I can then average those prime values spatially to get my eddy kinetic energy. So the first thing I do is compare to make sure what I get looks similar to what we get from an independent measurement, in this case, sea surface height. So this is the glider-based mean kinetic energy at 10 meters, the satellite-based mean kinetic energy at the surface. And if you look, those look broadly similar. Obviously, we don't cover as large of a domain, but the magnitudes are very similar. The width of the Gulf Stream is very similar. We see this feature of very low mean kinetic energy along the offshore edge of the stream. If we compare at these select cross-stream transects, numbered 1 to 4, so if we look at the blue curves, the thick line is from the gliders, the thin line is from the satellites. They agree quite well at 3 of the transects. At 1 of the transects here at Cape Hatteras, the glider estimate is a bit low. I think that's a sampling issue where our mean is not totally well constrained at every location yet, but still pretty good. If we look at the eddy kinetic energy, again, the agreement is pretty good. We see at the surface that we have high eddy kinetic energy along the core of the Gulf Stream. It's particularly large downstream of Cape Hatteras. This is where the Gulf Stream is meandering a lot, so it's going to have a lot of eddy kinetic energy. And there's also high eddy kinetic energy here at this little, this is a feature called the Charleston Bump. I'll show a bathymetry map later, where the Gulf Stream sometimes is deflected far offshore, sometimes not so far offshore. So we have a local maximum EK there as well. And we see some very similar features in the sea surface height-based estimates. And again, we get reasonably good agreement, particularly as in the values that they see key plateaus to offshore between the two measurements. Typically, the eddy kinetic energy is lower than the mean in the core of the Gulf Stream, but that flips once you get away from the core and on the flanks of the Gulf Stream, the eddy kinetic energy is larger than the mean. So it's good to know that the glider-based estimates compare well with the satellite-based estimates, but that's not really our goal. Our goal is to look at what the three-dimensional structure is, because that's what the gliders do pretty uniquely well. So now I'm showing you similar snapshots or similar slices through the field, but now at 200 meters for the mean and eddy kinetic energy, and at 500 meters for the mean and eddy kinetic energy. And then over here are on the same 4 transects. I'm showing the eddy kinetic energy in color, excuse me, and the mean kinetic energy contour. So the first thing to note is that the horizontal distributions are pretty much the same as we go down deeper, with but just with the magnitude decreasing with depth. It is worth noting that the maximum in EKE, so the brightest yellows here, are actually about 10 kilometers shoreward of the maximum of the mean kinetic energy. And we think that's because of the Gulf Stream is not actually symmetric. It's actually has a sharper gradients on the inshore side than the offshore side, so that meanders, as the Gulf Stream slides back and forth meandering, a shift of the same size is going to make a bigger difference on the side with the steeper gradients. The other thing just to note, and this is well known as well, is that the maximum velocity or the maximum mean kinetic energy shifts offshore as you move deeper into the water column. So because we see these magnitudes decreasing with depth, we might want to try and figure out an appropriate vertical scale for the kinetic energy, mean kinetic energy, whereby we might make a, given the satellite best estimates of the surface only, what can we infer about the vertical structure? If we know the rough shape and we know the appropriate scales, we might be able to do something like that. So what I did is I took all of the MKE and EKE estimates from the gliders, and I averaged them in a few different groups. So I averaged in the core of the Gulf Stream, so within 50 kilometers of the center of the Gulf Stream, and then on the offshore side and the inshore side. So the means here are in, or the mean kinetic energies here are in blue as profiles as a function of depth, and the eddy kinetic energies are in the shades of red. And so if you look at these, the shape of these profiles are all look pretty close to being exponentially decaying with depth. So the width of the width of each profile is a measure of the standard error of the mean profile, and I can fit to that mean profile an exponential plus actually a constant at depth. And from that fit, I can get a vertical scale, which are summarized here in the table. The take-home message is here. In the core of the Gulf Stream, that vertical scale is a bit longer than on the flanks of the Gulf Stream. So I have a slightly longer scale, order 300 to 350 meters in the core of the stream, and something closer to 200 meters on the seaward and shoreward flanks of the Gulf Stream. So that's what we've learned. That's what we've learned so far about the mean, the eddy kinetic energy. And let's see, Chris, how am I doing on time? When did we start?
Well, we started a little bit before noon, so and we normally, try to, if we started at noon, we'd probably try to end it at after 45 or 50 minutes. So
okay,
so just sort of
5-ish more.
Yeah, maybe
something like that.
5 to 10.
Okay, cool. So I'll talk just briefly then about these topographic effects. So I've mentioned, so this is just a map of the bathymetry showing a little more detail over the Blake Plateau. It's this whole region that's less than 1,000 meters deep. And particularly there's this feature here called the Charleston Bump that sticks out into the path of the Gulf Stream. And so when the stream runs into that, a lot of interesting things happen. And I wrote about this a few years ago in the early observations. We see these internal waves called internal V waves that form. So then the flow hits the bathymetry, it's deflected up, and then it oscillates near the buoyancy frequency. So periods of a few minutes. We actually detect that in an interesting way. We actually look at this is just a plot of the glider's depth as a function of time for a particular dive. And you see these wiggles in it. And the reason the glider should move very constantly vertically through the water because it's got a fixed buoyancy during ascent and descent. So these wiggles are actually due to the water moving up and down. So we can remove the glider's motion and we get this estimate of vertical velocity in the ocean. And these are vertical velocities of order of 10 centimeters per second, which is very large for the ocean. And you can see they're oscillating a few times per hour. That's very near the local buoyancy frequency. So we can average those all together, and we get this map that tells us it's about the magnitude of these internal waves using all the data we have. And we see these peaks, large internal wave sizes near the Charleston Bump. There's also something going down here off the near Cape Canaveral. At the same time, we also see thick bottom mixed layers. So this is another profile collected in the vicinity of the Charleston Bump. And this is in less than 400 meters of water. The bottom 120 or so meters are well mixed. So that's happening in the lead. So the stream is hitting this bump and doing a bunch of turbulence on the backside of the hill, and it's mixing the water column really well. So we see this. We see temperature, salinity, density, and velocity all very homogeneous. If we can measure those mixed layers, average again in these half-degree boxes, we see thick bottom mixed layers near the Charleston, or in the lee of the Charleston Bump, and also in this same general area off Cape Canaveral, where I suspect there's some bumps in the bathymetry that aren't resolved by this particular bathymetry product. The other thing that happens because of all this mixing, it actually forms these little small vortices called submesoscale coherent vortices. They're order 10 kilometers wide, so they're fairly hard to observe, but occasionally the gliders catch them. Then these are subsurface, you don't see them you don't see a signal at the surface. You can see it here as this spreading of isopictals, and it's got this is the velocity field, and you can see it in 2 dimensions here. You can see this thing is rotating anticyclonically at depths of 500 to 900 meters. It's homogeneous in the interior, so it's low stratification, and it actually carries, this is salinity anomaly along isopictals. This is unusually fresh water at that region. So what's happening is these, in the lee, this is now from the numerical model, in the lee of this topography, so the topography looks like an island if you take a slice at a certain depth. So this is that bump. In the lee of that, you're getting strong mixing, and it's also spinning things. There's the bottom friction happening that's making the water start to spin anticyclonically, and it takes water from the shoreward side of the stream where it's fresher, spins it up into the core of this little eddy, and then that eddy propagates downstream and actually works its way out into the ocean basin. So these little bitty eddies are actually contributing to the exchange between the continental margin and the deep ocean. So that was a pretty cool result, using the models to really get at the dynamics of these processes observed by the gliders. And then just a couple of quick slides on what we've been doing at Cape Hatteras. So the Hatteras region is an interesting region. This is why we had a big field program there, where the coastal waters converge. And it's also where the Gulf Stream is separating from the continental margins. You have lots of different water masses coming together in a small area. And the big question is, how much of this Middle Atlantic bight shelf water that comes down into the region, how is it getting out to the deep ocean? It runs into the Gulf Stream, has to make a left turn and go out. So I made, for 2 years, I had gliders going back and forth, more than 100 repeat transects along the continental margin from where the Gulf Stream separates to about 100 kilometers north. And from those, we built up a time series of this export of the shelf water. And you can see the main result there is it's really dominated by events. The mean is about a quarter spherodrip. It's very tiny compared to the order 100 spherodrips of the Gulf Stream. But the mean may be a quarter spherodrip, and that's a number we've known for a long time, but it's really dominated by these individual events that pop up that last, days to weeks. Some of those events are actually lined up with hurricanes, but that's not the part I want to talk about here. I want to talk about this period in the winter of 2017, 2018, when there was no export for almost 3 months. There was one little instance of a little bit of water came out of mid-Atlantic bight water types of fresh water, relatively fresh water. So that 3 months, if we look at a sea surface temperature image, so the warm, there's just 2 days, one in December, one in January of that winter, we see the Gulf Stream is really warm offshore, flowing to the northeast, but there's also this filament of water, warm water, that's come off the Gulf Stream. It's sitting and actually flowing northward along the edge of the continental shelf. That's the contour there. And what it's actually doing, if we compare, so this is on the left is the mean over the full 2 years of temperature, salinity, alongshore velocity, cross-shore velocity and alongshore velocity in the region. If we compare that to just that winter, we see that the water was warmer, much saltier than over the 2 year period. And if we look at the alongshore flow in particular, rather than southward alongshore flow like they're supposed to be, there was actually during that winter a pretty strong northward flow along the edge of the shelf. And actually the isopycnals were tilting the opposite direction, which in the end, so you had this Gulf Stream filament that was actually changing the structure so drastically in the region that it actually shut down the shelf water export in the Hatteras region for that entire winter. So that's just one quick example of the way the Gulf Stream can control what's happening with the shelf flows. And so from there, I will just say that now, so for 5 years, we've been running gliders in the Gulf Stream like this routinely. We're filling in the gap in the sustained western boundary current observations. And we've also gotten to get into quite a few new aspects of the Gulf Stream's variability and its dynamics. So my hope for the future is that this continues. It's a never-ending battle to keep things funded, to keep fieldwork going, but we've done 5 years plus so far. We hope to keep it going. That should lead to lots of new analyses, and I'm always looking for new people to use the data, working with them. And I can't leave off without noting that all of this fieldwork in particular has taken the help of a lot of people, particularly Patrick Dean, my tech here at Hui, and also the team at the instrument development group at Scripps, who help us dramatically with the glider piloting and glider maintenance. And then all of the different institutions along the East Coast that we have visited or called upon in emergencies to fetch gliders out of the water when things go wrong. And so just quickly, I'll say there are a variety of papers that we've had over the last few years covering all this, and also maybe more usefully, these are the references to the actual data, so both from the Gulf Stream and from the Beach program. So all of those data are publicly available and ready for use. And I'll leave it there.
Well, thank you, Robert. I guess for questions, what we can do is you can either use the raise hand feature or post a question in the chat. We already have one from Xiaoning Wu. Would you like to ask a question, Xiaoning? Sure.
Hi, Dr. Todd. Thanks for the talk, and I'll have more questions when we meet later. But just as starters, for one of the aspects that you mentioned in the study related to hurricane impacts, I was just very quickly, and a lot of interesting information in there.
Oops, sorry, we lost,
I need to back
lost
up
you there for a second.
Okay. So I was looking at the GRL paper regarding the hurricane impacts, and there are a lot of interesting ideas in there. One of the thoughts you mentioned is that this can be further tested with like numerical model. So what would be like the practical ocean resolution required to investigate some of these mechanisms proposed in there?
I mean, fundamentally, you need a model that gets the Gulf Stream right, which is a significant challenge for numerical models. The Gulf Stream is only about 100 kilometers wide, so at minimum, you need several grid points across the stream. So you're already down to a model of order 10-kilometer resolution. It would, in all likelihood, well, I suppose you could probably get at this with a non-assimilating model that you just stuck a hurricane into, but you would still need realistic bathymetry, or realistic enough bathymetry that you could look at things. The various coastal trapped waves are a big part of what's propagating the signal. Things like Hurricane Maria and Hurricane Jose were actually well upstream of the Florida current, but I didn't show it, but there were measurable decreases in the transport in the Florida current. So there has to be some mechanism to propagate that signal from against the Gulf Stream, which the coastal wave guide is one of the obvious choices for that. So it would not be a global model. Let's say that it would be a regional model that's been somehow forced to have a good enough Gulf Stream, and it would have to be a coupled model, probably. So, well, maybe not, but it wouldn't be. It's not trivial for sure.
Thanks.
Okay, we have a question from Joe Warren.
Hi, Robert. Really great talk. I had a question about when the hurricane caused the Gulf Stream transport to be reduced. Does that water pile up south of the hurricane's path, or does it get squirted up onto the shelf or outside your glider transect?
That is a very good question that I don't know the answer to. That was one of the open kind of questions with all this, because our observations are pretty spatially limited during that short time of, where did, volume conservation says that water went somewhere, but we don't know where it went. That's, yeah. And that's another question, actually, that a model might help us get at, because a model would have information everywhere.
Thanks.
So I have a sort of a follow-up question. Do your observations allow you to determine how long it took it to spin back up again after it had the reduction?
Coarsely, and that's where we say something like 2 weeks. It wasn't very long. So actually, the better thing to look at is the cable data also showed a slowdown there. And actually, Hurricane Matthew was a particularly dramatic one. Actually, I think Dorian last year also made a really, because it went right over the cable, basically, made a very dramatic one. But those tend to be order a couple of weeks, kind of, before things bounce back. Seems to be the kind of time scale. We say that from the glider observations because after 2 or 3 transects, each transect taking order a week to occupy, things were back to looking normal. So we can sort of bound it by that.
It'd be really interesting to see how far upstream and how that affected the Gulf Stream. Mary Scranton has a question.
Yes, this is Roger Flood.
Not Mary.
So she's right here if you want to say hi. Anyway, so my question had to do with the deeper water masses that you mentioned. And I was curious if you could detect any Mediterranean water in there.
We have not, so no is the short answer. I don't know offhand. I'm trying to, oh, that's where where's my TS diagram? There. I mean, the Mediterranean water would be obviously very salty, and tends to come in at sort of the mode water, intermediate water depth. So my suspicion would be that by the time you get all the way across the Atlantic, especially into the Gulf Stream, because a lot of this water is actually coming up, has actually taken a much longer route in the stream, that any distinct Mediterranean water signal was going to be absorbed into, one of the mode waters or one of the intermediate waters. I'd be pretty surprised to see say an intact Medi make it all the way to the stream.
But so I guess if we're looking for the bed water, you would actually want to, following up on what you said, you'd want to be looking at the water that was not in the Gulf Stream that you sampled.
Right.
Okay.
Right. Yeah. Yeah.
Right.
And actually, by construction, this transport thing is limited to what we identify as the Gulf Stream.
All right. Thank you.
So I have a few questions that might be considered general enough to just ask now. So one of them is about this massive Lee wave, and I mean, considering there's a numerical model study of it, I guess it's been looked at. But do you have any sense for how this impacts the momentum and energy balance of the Gulf Stream?
So we did it so actually, I should say first that the modeling here, we did not get into the Lee waves in particular. This was focused on the bottom friction and the mixing and the vortices that form. But I did in the 2017 paper I wrote, I did make as much of an estimate as I could of the energy you can estimate the energy of these waves based on the amplitude of the waves. And let's see. The answer with fairly large error bars, the answer was that these Lee waves are somewhere in the 10, maybe to as high as 50% as energetic as, say, the tidal waves forming off the Hawaiian Ridge. So it is significant energy. It's still a small number compared to the kinetic energy of the Gulf Stream.
Okay,
this is energy transferred from the large scale flow to the small scale, but it's not a big chunk of the Gulf Stream's energy going into those waves. And likewise for the bottom mix layers, there's in doing mixing, you're raising the center of mass of that mixed layer. So you're increasing the potential energy. So you're taking kinetic energy and moving to potential. But again, it's in sort of the same ballpark size as the Laye wave. So it's real, it's there, but obviously it's not stopping the Gulf Stream by any stretch of the imagination. The Gulf Stream is still picking up steam as it goes through there and increasing its kinetic energy as a volume integrated quantity.
And there's one thing that I just had a question about on slide 9. If we can get back to there. This is about the oxygen distribution.
Oh dear.
About it. So you've got this, so this is at 36.
This is
so this
36 after it separates from the coast.
Okay.
Yep.
And you've got this, maybe I can annotate. So you've got this minimum layer here, and then you've got a subsurface maximum. Do you know where those come from?
So the subsurface maximum is the upper Labrador seawater, and you can actually see in the it's the very top of the upper Labrador seawater.
Mm-hmm.
If you look in the velocity field, you actually see there's oppositely directed flow tucked in here under the Gulf Stream. So this is north of Hatteras. So this is before the deep western boundary current, which carries the upper Lab seawater, before it has crossed under the stream at Hatteras. So they crisscross at Hatteras and switch sides. So that high oxygen is consistent with the upper Labrador seawater. That's relatively new water. It's only a few years to get to transit from the convection regions of the Labrador Sea along the continental margin to get here. So that's why that is high in oxygen. This low oxygen water, let's see. Well, Antarctic intermediate water is low in oxygen because it's old. It's taken a long time to get there. At this latitude, I'm hesitant to say that that's actually, there's that much Antarctic intermediate water visible in this section. I have to see it in TS space which water we're in. This may just be other older intermediate waters, basically. And then, of course, you get back towards higher oxygen out in the relatively recently formed mode waters and up near the surface. But yeah, I know that's the up to Lab seawater coming down.
Okay, cool. So we'll take one more question and let people go, and then people who want to stick around can continue to chat. But we have a question from Kamazima Louisa.
Hi, Robert. Thank you very much for a great talk. My question is regarding when there's a slowdown on the Gulf Stream. Have you looked at how much of an impact it is to the sea level on the coast?
So I haven't looked in too much detail. In that same paper, I didn't throw all the figures in here because I clearly had a lot already in there. We did look at the tide gauges for this particular event, and you can very clearly see in the tide gauge records the storm surges, but that's not what you're asking about. You're asking about as the stream slows down, has to also be a reduction in the cross-stream sea level tilt, and do we see a signal at the coast from that? And we couldn't, from these particular storms, we couldn't pick out much. I know there's been a fair bit of there's been some debate in the literature about that. In the southern, so south of Cape Hatteras, there's a fairly direct connection between what the sea level is doing in the stream and what's doing at the coast. Things get a lot more complicated when you get downstream, and because now you have the sea level slope of the stream is way out here, and you have both the slope sea the slope sea recirculation happening in here, which has a sea level signal, and you have the shelf break front, which itself has a sea level signal. So it's a lot more complicated downstream to figure out how the sea level gradient across the stream is going to impact what the coastal sea level is. But yeah, I have not looked in great detail at it from these particular events.
Thanks.
Okay, well, we'll just wrap up. We can see, how do you do this? post a little clap emoji or whatever. Thank you all for coming and to this talk, and for the students, please remember to answer those questions and send them to me. My email address it should be on Blackboard, but it's christopher.wolfe@stonyBrook.edu. And we'll see you next week, or most of you.
Thanks.
Yeah, I pitched this to my my foundations of marine sciences class, because on Monday we did a section on, or was it last, I don't even remember time anymore. But I did like a little section on methods of observations in physical oceanography, and so go through all the standard stuff, CGTs and da-da-da. Is like, and then we've got these gliders, and we're gonna hear about them. So
that's convenient. That was convenient. Yeah.
Well, we actually, so in previous years, we have had we do have a glider now, and Charlie is probably going to talk to you about that in a bit. But and so like last year, we actually had people like go over and look at it, and Charlie gave a little spiel about it, but now like we don't go places and gather in small spaces. Plus the glider at the moment doesn't work. And that's the problem with having one glider, is that I imagine that there's a fair fraction of yours at any time that don't work.
A smaller fraction than if they were a certain other make of glider.
So you've got the spray.
I'll say that. Yeah. But yeah, I have 8 sprays in my fleet, and we tend to keep 3 or 4 at sea on average. But that's just churning and refitting them between missions. But things happen. Sharks happen. Breakages happen. I did not include the
question. Oh, and at this point, we're not doing regular questions anymore, so anyone can just chime in and say what they want to say. So Charlie, if you want to ask about flow past Cape Hatteras, you're welcome to do so.
Hello, Robert. It was really nice to hear this stuff. I've been following it sort of loosely over the years, but it's really nice. Cool. I have some more questions when you and I get to talk later, but in the Peach data set, and during that period when there wasn't any flow leaving the shelf, I assume that the flow down to the south continued and disappeared into the South Atlantic bight. That has happened in the past.
Yeah. So we've done a little more looking into this. So there's a student at UNC, one of Lujan, one of Harvey Symes' students, is looking. She's looking at actually this particular little squirt right here in mid-January. So there was, and it's actually timed with this SST image here. There was a little squirt of water that went out very much subsurface. I'm actually looking at it as sort of a gravity current kind of flow. There was a big nor'easter went through. The water got really cold and became dense enough to go under the Gulf Stream. So that's, some of it went that way. You can kind of see in this SST image that the cold MAB water has gotten around past Diamond Shoals, but it doesn't go, in this particular time, it doesn't look like it went really far south. As you said, there have been cases where you see the mid-Atlantic bight water reaching like most of the way down towards Cape Lookout, for instance, but it didn't seem to happen there. There's actually in Churchill and Cornillan's paper, they look at a bunch of instances from the SST imagery, these filaments, and they posit, and I suspect they're generally right in that at wherever the northern extent of these filaments are, you have Gulf Stream water again meeting the slope water in a sort of so you have in a long stream gradient, the slope water is denser water. There you again get the right density orientation of the density gradient to get offshore flow again. So the suspicion is that a lot of the flow that would normally have been coming out in the Hatteras region was actually heading offshore well to the north. You can see the filament up towards 38 north. So we suspect there was some more than usual export of maybe shelf water in the middle Atlantic bight during that period as well.
Okay, that sounds reasonable. I also note that mid-Atlantic bight is often sort of intermediate in density between surface Gulf Stream and so sometimes you see it as forward water at the surface where it's really low salinity, but oftentimes it takes off at some sort of intermediate depth.
Right. Yeah. And actually, I didn't show an example of it here, but I've got lots of beautiful transects from the gliders where you can see this subsurface forward water that's even well down. Sometimes even down at 37, 38 north, you still see salinities 34 or less in these little pockets right tucked into the north wall. Yeah.
That sounds like the old filaments that the Red Right used to track. Anyways, yeah. No, I'm getting old. I forget what they called them, but they were very prominent in cross-shelf sections.
Right. Yeah.
Okay, thanks.
Yep.
So with this, a few more questions. With this Labrador seawater, that's stuff that gets picked up at Cape Hatteras, is that right? Or does it come in a little earlier?
So let's see, where is that? Back to the right. So we actually start seeing it coming in. So Hatteras is actually way down here. So we're actually seeing it come in over the Blake Plateau, and
How's it even getting up there?
Well, so that is a very good question. Here's a convenient spot to doodle. Hang on, I have to. All your lovely pictures are blocking my access to the annotation tool.
Wait, what?
I got it. I had moved your pictures around and it was blocking the
Oh, okay.
my access to the pen. No, it's not happy today. Maybe I can draw. Maybe I can't. I lost my mouse.
Stopping you? I might.
No, it's my mouse is being stupid.
Okay.
There we go. Okay, now I can draw. Yeah, so what actually seems to be happening is, so the deep western boundary current is flowing, generally speaking, following the deep slope out here. So the crossover point, it's come down from the north up here, that crosses the stream at Hatteras. It looks like somehow there is upper lab seawater that is getting peeled off all along the Blake Plateau. And we see instances of right along the bottom of when the gliders get out here, we will see. Now we are not getting the core of the upper side. We're seeing the very tippy top of the upper lab seawater. We've had a number of discussions with Nigel and Andre. So is it really upper lab seawater? But it's the top of it. We're certainly not seeing the full extent. I mean, most of it is down at 1,500 meters or more where we're not sampling. But somehow that water is getting. So there's the Antilles current that's sort of not very steady at all flow.
Right, and you actually
north
see
of the Bahamas.
transport, because those people will debate as to whether it's there at all.
I can see why, because the last couple of years we've had clearance to go into the Bahamian waters, and the gliders typically leave Miami. Change colors. Orange is good for a glider. Leave Miami and then they end up just about at the northern end of the Bahama Bank, and then I'll typically send them out here somewhere, and sometimes the flow is to the southeast, sometimes it's to the northwest.
Okay.
So I think there's a lot of reaction happening right in there. So it's hard to say what a mean Antilles current really looks like. And there's also flow coming in through the Northwest Providence Channel as well, that's included in our the transport we get from this first outbound transect. But yeah, there seems to be something. It's got to be some eddy-ish thing that's allowing this upper lab seawater to get up onto the Blake Plateau. So it's very much it's doing all the things it's not supposed to do. It's crossing F1H contours. It's moving up into shallow water. But that whatever's happening out there is right at the outer limits of where we sample. So we're going to have to. We thought about seeing if Argo can help us a little bit, but I suspect it's mostly going to fall to. Do models tell us anything? Do models get this happening? And if so, what do they say about how it happens?
I'm not. I have no idea. But it is kind of. I mean, it's got to be some sort of boundary layer process.
Right.
I mean, you had of course, I was in the lead of the Charleston bump, but you had 200 meter thick
right
mixed layers.
Yeah.
So there's definitely a lot of dissipation going on.
Right.
So then you can flow across topographic contours willy-nilly. Cool. Well, let's see if anyone else. So I already had you, and then we're gonna talk a little bit later. Did you want to do that over Zoom or FaceTime or whatever, or what?
We'll figure it out. One of those. Yeah.
So if anyone else wants to chat, they can chat. But otherwise, if we can all break for lunch if you'd like. And I think Charlie is set up to meet you.
Yep.
Hi, Robert.
Okay. There's one
Hi,
question.
Robert. Amanda. Nice talk. I was very interested in your talk about the coherent vortex observations. It looks like that your glider went right across the center of that vortex.
For that particular one, yes. By no particular fault of my own. It just happened to go through it. We weren't actively seeking it out or anything. Because we wouldn't have known where it was to begin with. We just had to happen across it. But yeah, we did go very near the center of that one.
So is the very sharp turn that it makes when it gets into that coherent eddy?
So what I'm showing, so the vectors here are I think depth average current between 500 and 900 meters. So which is between these two isosignals basically that I'm showing that are spread apart. It so happens. So this is not something I was looking at in real-time piloting. But you can tell also that the full depth average currents were reversing there. So that's typically when I turn around as a piloting strategy of, okay, if the current's now going south, I've made it across the Gulf Stream. I can turn around now and go back. So it was purely happenstance that we went back later. And actually, I was not the one that spotted this eddy. It was Jonathan Gulla, who's the numerical modeler in Brest in France. Had spotted it in the observation by going through and looking for, isopignal spread, and then I went and looked, and indeed you could see it in the velocity field as well. So these things are so small, and with no surface signature, there's no way for us to go seeking them out specifically. We just happen to happen across them, and because the gliders sample every 5 kilometers or so, we can resolve them. And you see it's only a few profiles. If it's 5 kilometers or so between profiles, we've got, at most 20 kilometer radius of this thing.
If it happens to catch one, can you just make this glider just stay in it for a while?
In principle, depending on we'd have to notice it in real time, and it would depend on it's kind of the problem that the Argo floats have a similar problem of, because they always have to be going up and down. When they leave a feature like this, you don't, if it's quite small, you don't necessarily know that you're going to land back in it when you move, say, like for instance, at the earlier state, like in the earlier stages of the formation of these, like the one circled here in yellow in the model, a glider might pass through that, but that's right in the core of the Gulf Stream. Like by the time the glider heads up to the surface, it's going to move many kilometers from where that subsurface feature is, and it's not going to hit it again, and not going to be able to get back there because of the strong flow. So it's hard, mostly because of the ambient flow field around it.
Okay.
Yeah, Wenda's really into eddies. He's been trying to diagnose diffusivity by tracking eddies around.
Okay. Yeah. I mean, I should say we see like almost every section, every time we cross the stream, we see these co-rotating eddies. So not the warm core rings and the cold core rings; those are rotating in the opposite direction of the stream on either side. We see ones that are doing this along the edges. So pretty much every time a glider gets to the edge of the stream, it finds this flow that's wrapping around the other way on the edge. So you see that in the glider trajectories. If we stare at the movie again, which doesn't seem to want to play. Ew. There it goes. If you watch the ones when they start going from the south, they often get to loop upstream, and it's often because there's an eddy there. There's an eddy it's going around, a little eddy it's going around the edge. So it seems these sort of frontal eddies, for lack of a better description, are pretty ubiquitous, as in addition to the big warm core rings and cold core rings. So it gets back to the why it's hard to define what the transport is. How much of the eddy counts as Gulf Stream transport? How do you define the throughput versus what's just recirculating locally? But yeah, these to control this thing. Apparently, I don't have control of the movie, but anyway.
Oh, yeah, these submesoscale eddies might be hard to be observed, but
Right.
some bigger ones like the Gulf Stream rings. So those maybe you can.
Oh, those I actually have a glider out right now that's spending time in the ring that's southeast of Nantucket right now. It's just about completed its first transect all the way through the ring, and then it's going to dive back in, and you end up spiraling in and out of the ring basically. We've done that some. I did it a little bit last year and done other times. This particular glider, I'll let it do it for a month or more to get a good picture of what this ring looks like.
Wow, that's cool. And I remember before I even noticed some studies they put like maybe a couple of gliders maybe together into an eddy and make them follow the eddies. And,
so the group, particularly the group at the University of Washington, does that a lot, where they have done they often do a one of their common modes of operation is to put a Lagrangian drifter in an eddy or in a front, and then they fly the gliders sort of in a bow tie pattern back and forth, tracking in Lagrangian sense the drifter, so they can follow a feature. Yeah.
Okay. Okay, great. Thanks.
Yeah, I'm looking at that cold core eddy.
It's the warm core one I'm in.
Oh, there's a warm core. So that would. Oh no, sorry, it is a warm core because it's on the north side of the Gulf Stream. Obviously, it's just.
There's two of them out there. I'm in the one to the west, the closer one.
Yeah.
The other one's in Canada, and I don't have permission.
Oh. Cool. Wow. Let's see. Who do we have still on? We just have a handful of people on. if anyone else wants to pipe up, you can pipe up. Otherwise, let Robert go grab some lunch. And I would grab some lunch too.
Lunch is always good.
Maybe one more kind of, it's a half a question, more amusing than a question. I know the data is a bit too short for this, but do you see any indication that the Gulf Stream is in some way being controlled by the NAO?
I don't at this point see. It was only 5 years.
Yeah.
I can't say anything. You know, the one of the right guys to ask that question is one picture above you on my screen. He's got his hands on a long enough data record that might be able to address that.
Yeah, I mean, so there are correlations there, and then I've talked about we had a visiting scientist in Chapuis who was doing adjoint modeling of this, and he was trying to figure out how actually the correlations arise. And what it seems to be is that the Gulf Stream, it moves back and forth associated with, north and south at least, associated with changes in the NAO. But most of that seems to be due to changes that are happening kind of right on top of the Gulf Stream. And so the changes in the NAO cause changes to the wind field, and that's not, and that's sort of to the southeast of Newfoundland and Labrador. So it's kind of right there on top of the Gulf Stream. And so it's not where you normally think of the NAO as having an impact, which is sort of further north and east of that, but there is a small impact on the wind field there. And it's sort of in the right sense to cause, upwelling, which can cause the Gulf Stream to kind of migrate northward and downwelling, vice versa, that sort of thing. So, whereas, and it does it with a relatively short lag, which sort of makes sense because it's really close. A lot of the older theories of the NAO Gulf Stream interaction assume it's these large, long planetary waves that are being launched, in the middle of the Atlantic, and they should take years to get there, and you just don't see that kind of delayed response. And so I think it's very much a local.
Right. And I suppose these reduction of speeds from Robert's work kind of sort of, not quite, point to that, right? That the immediate winds have much more impact on the Gulf Stream. Yeah. Thanks a lot.
Tremendous momentum input to slow down that much water by so much.
Yeah. Yeah.
Yeah, to almost 200 meters, something like that.
It was the full water column.
It was
600 or 700 meters. Yeah.
Wow.
It was slowing full depth over the plateau. Yeah. There was both a barotropic and a baroclinic part to it. There was more intense slowing at the surface, but there seemed to be real slowing at depth as well.
That's some breaks.
Yeah. So yeah, a lot of momentum input to do that, or extraction, or however you want to look at it.
Yeah, because maybe it spun up the storm.
Well, it may have been more of a water level issue rather than a direct frictional driver.
Right. It might have, yeah.